last time we did an introduction to the heap sort, mainly the background, why we need to do the heap sort. Today we start looking at the data structure, the heap data structure. Yeah. So then algorithm. Yeah. All right. So 8.3 heap property. Yeah. All right. So let me play. Yeah, this 8.3. All right, yeah. No. Relationship among heap nodes. Remember, we need to find a way to represent parent-child relationship in a heap. Yeah. And we do not want to use linked lists. Yeah. We want to use some simple way, no concrete links. No concrete links. Yeah. Yeah. Because that could be very complicated. So we want to avoid the complexity of the concrete links. Yeah. Right. A binary tree is stored in an array. Yeah. By imagination. Yeah. Because you cannot see a binary tree. Yeah. But there is a, imagination of binary tree. Yeah. But although it's an imagination of the binary tree, but it has all the properties of a binary tree. Yeah. The root node. Yeah. Then under the root node, the first level, two child nodes, the first level, second level, and so on. Yeah. All right. Node, yeah, so here we do observation. How do we identify a node by its index? Yeah. Each node, yeah, we use the index number. We can uniquely identify the nodes. Yeah. So here you can see the index is important. Index number is important. Yeah. So when we control the index numbers, we can control the nodes. Yeah. And we can access the node locations through indices. So we can access all the nodes through indices. Yeah. All right. So that's our understanding. So then, when we study the relationship between two nodes, can we study the relationship between two indices? Yeah. Two nodes, they have their corresponding indices. How about we just study the relationship of those two corresponding indices? That's simple, right? Yeah. That's simple. Yeah. All right. All right. Now let's study the relationship between two indices. Yeah. Parent-child relationship. We'll look at their corresponding indices. Yeah. All right. Yeah. P node, P colon I, that means the index of the parent node is I. Okay? Then left child, capital L, left child, and the right child. Okay? The left child, we use 2I index. How about that? Double the index of the parent index. Then right child, we use 2I plus 1 index. How about that? That's a simple way. Simple way to define parent-child relationship. Yeah? In this way, we do not need to use any link, right? No concrete link needed. Right? A parent-child relationship. Yeah. And in this way, you can see, yeah, this looks like a perfect way. But when you use this way, one little thing you need to be careful. That is, you cannot use I equal to 0. That node you cannot use. Because if you use that node, I equal to 0, double it, still 0, right? Yeah. So when we double the index number, we should get a different number. So for that reason, we need to assume I cannot be 0. That means the first location, we cannot use it. We cannot use the first array element to store any node. Yeah. Leave it out. Yeah. So starting from node with index 1, 2, 3, 4, 5. Yeah. Yeah. For the technical reason, okay, yeah, we cannot. Technical reason. Yeah. Other than that, then you can see it's perfect. Yeah. Because if you skip the 0 index, yeah, yeah, one element is wasted. Yeah. If you do not feel it's a big deal, it's not a big deal. Yeah. Then everything else is perfect. Yeah. Why perfect? Yeah, because in this way, if you use this way, you do not skip any node, right? Can you imagine? If we use this parent-child relationship, all the nodes are used, right? There is no node. We skip it, okay? Yeah, because you double it, you skip many, but other nodes, okay, you double. You cover all the nodes, right? Yeah. Yeah. Because 2i even number, 2i plus 1 odd number. Because all the integers, you can divide it into even and odd, right? So all the numbers are covered. You do not miss anyone. Yeah. All right. Yeah. So that's, in this way, we can use an array to store binary tree. Yeah. Parent-child relationship. Yeah. From the child node, one child node, you can access its parent. From a parent node, you can access 2 child nodes. 2 possible child nodes, right? Because some node may not have the right child, right? Some parent node, not because the bottom level may not be full, okay? Near complete, remember, the heap is a near complete binary tree. So the bottom level may not be full. Yeah. Yeah. So, yeah. If you hit the level, just one level above the bottom level, so then a node in that level may not have a right child, right? Yeah. Even left child. Yeah. So here, I can draw some simple example. Another level. Yeah. Then the next level, not full, right? Not full. Okay. And I can draw another one. Okay. So this node only has a left child, no right child. But this node, no left node, no right, no child. Yeah. All right. Yeah. See. Yeah. All right. So then, okay. Yeah. Yeah. About heap nodes, 2 types of heap. Then, after we specify the parent-child relationship, then we need to add another important property to these heaps. Yeah. Yeah. So 2 types of heaps. Yeah. Max heap and the min heap. Yeah. Maximum, minimum. Yeah. Yeah. The max heap and the min heaps. 2 types. Yeah. Right. Because when you sort array, you need to use there are two ways, ascending order, descending order, two directions. Yeah. So that's why two different types of heaps. Yeah. Yeah. Max, yeah. So from this name, the max heap property, that is, the value of the child node should be greater or equal to the values of both child nodes, left, right. Yeah. That's the max heap. Yeah. Min heap, just the opposite. Yeah. Less than equal to. Yeah. 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 And we know these two just symmetric, right? Yeah. Yeah. You change the direction of your inequalities. So in this class, we only study the max heap. Yeah. That's enough. Yeah. Yeah. All right. All right. So then, next, let's look at a simple max heap example, yeah, to give you some visual understanding on a max heap. Yeah. Given an array, yeah. All right, look at this array. Yeah. First, let's check, is it max heap? Yeah. So the value, in the circle, that's the value of this node. Yeah. Outside, that's the index number. Okay, 1, 2, 3. See, that's the index number. 1, 2, 3, 4. In that order. Then inside the circle, the number, that's the value of the nodes. Yeah. So, yeah. For each node, so each triangle, you can check. Yeah. So parent, child, triangle, you can check the max heap property. 16 greater than 14 and 10. Everywhere. You need to look at it everywhere. Okay. Yeah. Everywhere. Yeah. All, satisfied. The max heap property is satisfied. So we call it, this is a max heap. Yeah. All right. Then, yeah. Yeah. So here you see this max heap in a binary tree structure, but your actual storage, you won't have that binary tree, right? So your actual storage is still in an array. Yeah. There is no specific, that object, yeah, binary object there. Yeah. So what you really have is this array. Yeah. Array, yeah. 16, we put in location 1. Yeah. Then 2 child nodes, yeah. Location 2 and 3. Yeah. Parent child. Yeah. Then node 2 child nodes, yeah. 4 and 5. Yeah. So node 3, 2 child nodes, yeah. Node 3, yeah. 6 and 7. Okay? All right. Node 4, 2 child nodes, 8 and 9. Okay? Node 5, only 1 child, 10. Yeah. So in this way, yeah. So you just store a max heap in an array. Yeah. And the connection based on the, the values of the numbers, right? Yeah. Based on the values of the numbers. Yeah. Index numbers and the values of the elements in the array. Yeah. So, yeah. All right. So max heap. After you understand this structure, next we need to work on, remember, the 3 requirements. We need to use this data structure to do the sorting following the 3 given requirements. All right. Maintaining the heap property. First, we need to study some basic operations. So, what do you mean maintaining the heap property? Remember, we use this heap to store dynamic data. Yeah. Think about when you insert a new element into the heap. After the insertion, How do you do insertion? Let's think about. Yeah, suppose we have a heap. Yeah. Let me still draw a simple heap. Yeah, in this way. Suppose this is our current heap. Okay. Now, let's assume we need to insert a new element. Into the current max heap. Yeah. After insertion, we want to recover it to another max heap, also max heap. No. We don't want to break the max heap property. We still want to maintain the max heap property. All right. So this new node is inserted. So then we need to, you know, we need to put somewhere, right? Yeah, we need to put somewhere. Yeah. So think about, where do you want to put this new element? Which location is the most convenient location to put this element? Is it this one? Is this location the most convenient location to put, right? Yeah? Yeah. But after you put it, it's very likely the max heap property is violated, right? Yeah. Yeah. It's very likely the max heap property is violated. Yeah. Then, what should you do if the max heap property is violated? Think about what you should do. You need to fix it, right? You need to fix it. Yeah. Yeah. So the question is how to fix it, how to recover this max heap. All right. So that's how we talk about maintaining the max heap property. The operation, we need to answer that question first. Yeah. All right. Yeah. When the heap property is violated due to some operation, insertion, deletion, etc., how to fix it? Yeah. We answer this question. Yeah. All right. Yeah. Let's look at the one typical region. Yeah. This, triangle PLR, triangle, local triangle. Violation occurs locally. Yeah. 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 If violation occurs locally, how do we fix? All right. Yeah. Violation, that means the max heap property is not satisfied. Yeah. All right. So we need to fix. Yeah. All right. So here we can assume, this L subtree, R subtree, they both. They are max heap, subtree. All right. All right. Then let's do the local fixing operation. Yeah. All right. And after we do the local fixing operation, we need to check for violation globally, right? Yeah. Because after you fix violation locally, the violation could propagate, right, to other places. Yeah, because you move the nodes, you change, swap, so the violation could go down to other places. Yeah, go down to other places. Yeah. All right. So for that reason, you need to check other places also. Okay, globally. Check globally. Okay, all right. All right. Recursion approach. Local heapify. We call this a local heapify operation. So here we use a recursion approach. Yeah. Yeah. Remember, last time when I talk about in-place algorithm, still remember in-place algorithm concept. Yeah. I said one thing. Because in place, that means the extra space used must be bounded by constant, right? Big O of 1. Yeah. Big O or big theta, the same thing. Yeah. Similar. Yeah. Big O of 1 or big theta of 1. Yeah. In place algorithm. Yeah. Then I said if our algorithm contains recursion, then the extra space used cannot be bounded by constant. Yeah, because recursion, there is a stack. Okay, you need to use a lot of memory space to store that stack. Stack could be very deep. Yeah. That's the problem. Yeah. So here, although the recursion approach, but after we understand the whole process, yeah, when you write a code, you need to use for loop to replace the recursion. For loop. Yeah. For loop, then we do not use stack. If you do the recursive function call, you need to use the stack. Yeah. Yeah. But in our understanding, we can use recursion to understand. Yeah. Implementation, yeah, we want to avoid recursion. Yeah. All right. Now, so look at this. PLR, this local region, we want to fix the violation of the max heap property. Yeah. All right, let's look at the pseudocode. Yeah. All right, first we compare A of I value. Yeah. So if the A of I less than A of 2I, that's a violation, right? A of I less than A of 2, it's a violation, we detect it. After we detect, we find a violation, then we need to prepare to swap the value, right? Yeah. Swapping. Yeah. Swapping. But here, yeah, when we do this small operation locally, we want to do it efficiently. We want to do it efficiently. Right? Think about how to do it efficiently. Yeah. All right. After the first comparison, we find the violation is found at this place. Yeah. Now, what do we do? Yeah. Here, we do not do swap immediately. Yeah. We do not do swap immediately. We store. We use a variable called the largest. We store the index number 2i into that largest variable. This largest variable, you know from its name, you know, we want to store the index of the largest value in these 3 nodes. Now, which index? Among these 3 nodes, P, L, R, these 3 nodes, which one has the largest value? So that index number we want to store in this largest variable. Yeah. All right, so after the first comparison, we store 2i in this largest variable. All right, not enough. We need to do more comparison. Okay, all right. Else, yeah, else, yeah, because no violation, right? No violation, we store I to this largest. I, that value larger, parent value larger. Okay, all right. Yeah, so that's the first comparison. This is the first comparison. Yeah. Not enough. We need to do second comparison. Second comparison, compare. If A of the largest, largest, this time we compare largest. A of largest less than A of 2i plus 1, yeah, another violation, right? The second violation. Yeah. Then we should update the largest value. Largest equals 2i plus 1. Yeah. L, yeah, otherwise we do nothing. Yeah. Yes. So All right. Yeah. So after two possible violation detection, okay, two possible violation detection, that's enough. Okay. Now we need to prepare. Next round, we need to prepare for the swapping operation. Now we are ready to do the swapping. Okay. All right. But before you do swapping, you want to check if the largest is not equal to I or not. If not equal to I, then you do swapping, right? If equals I, that means no violation, okay? Because your parent node has the largest. Your parent node has the largest value, then no violation. Yeah. Yeah. So if largest not equal to I, yeah, you have a violation, so you need to do one swap operation. Yeah. What swap operation? Swap between these two nodes, the parent node and A of largest node. That's swap operation. After that, you fix the violation locally, only in that 3 nodes triangle local region. Outside, you don't know. Okay? Yeah. But in that local part, you fix it. Yeah. So that's what we call local heapify operation. Yeah. So this pseudocode, that's the local heapify operation. Yeah. All right. Next, 8.4, heap example. Yeah. Now, with this local heapify operation, now we want to see when we have a violation, how do we fix it? How do we fix a violation globally? And locally, it's not enough. We need to fix the violation globally. Yeah. Yeah. Here, I use a heap example to show you. Yeah. All right. A max heapify example. All right. Yeah. Here, in this example, I use the color, gray color, to tell you there is a violation here. Yeah. Because the value 4 less than 14 and 7. Yeah. So we need to fix it locally. Okay? Yeah. All right. To fix it, yeah, in this triangle, this node has the largest value. If largest, we should do swap between these two nodes, right? Swap operation. Yeah. All right. After the swap operation, yeah, yeah, in this local region, it is fixed, but yeah, remember the problem can move down one level. Yeah. So here I use this gray color, so I can call this node a dirty node. Yeah. Dirty node. So this node has some problem. Okay. So when you move down this dirty node, still dirty, right? Yeah. We still need to check. Yeah. We need to follow this dirty node. Okay. Even if we move it down, we still need to follow this dirty node to check its local triangle region and see if there is any violation. Okay? Now when we check another violation, okay? And this node, this 8, this, we need to do the swap. Okay? Swap operation. All right. Now another round swap operation, when this dirty node hit the bottom, yeah, because we hit the bottom, then nothing to worry about, right? So when a dirty node hits the bottom, it becomes a clean node. Yeah. Yeah. So it's not dirty anymore. Okay? All right. So we fix it. We follow that, dirty node all the way down to the bottom level. Then, yeah. We're done. Yeah. Or otherwise, not necessarily you hit the bottom. If somewhere in the middle it's not there, you check the violation, no violation, then then you can make it clean. Yeah. 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 Clean node. Yeah. Yeah, because local region, there, you do not need to worry about, because before the violation, we assume, before that violation, we assume the whole max heap is a good one. Okay? Yeah. Yeah. Only, some problem occurs locally. Yeah. One location, one specific location. Yeah. All right. So that's the max heap part. Then next, we want to look at the example, building a heap. It's important because think about when we start, we are given arbitrary array, right? Arbitrary array, it's not a max heap. When you start, you have an arbitrary array. The question is, how do you convert it to a max heap? You need to do a lot of work. Convert an arbitrary array to a max heap. Yeah. So that's the building a heap process. Yeah. Build. Yeah. Yeah. All right. Yeah. So let's look at that operation. Yeah. Yeah. Here, suppose we have a random array like this. Yeah. How do we convert after some swap operation? How to make it a max heap? Yeah. So next we need to do that operation. All right. Yeah. Yeah. First, let us arrange it to a heap structure. Yeah. Yeah. So this is a heap structure without max heap property. Okay. Yeah. Yeah. Without max heap property. So now we want to build the max heap property into this heap structure. All right. Yeah. Then, now, let me show you the process. Okay. All right. All right. So when we start, so because when you look at this question, you need to look at this question in a global way, not a local way. Yeah. Locally, you have the max heap property. That's not good enough. You want to make sure globally you have that max heap property. Yeah. Okay? The question is, how do you make sure your heap is a max heap globally? Yeah. Yeah. Okay? All right. Yeah. That's the main question. Yeah. All right. Yeah. Now, let's check. Let's scan this heap. Yeah. Following certain order. The order is important. Following certain order. Order is important. Check for violation. When we do the checking, we check local triangles, right? Different local triangles. Yeah, yeah. But when you check the local triangles, which order do you want to follow? You need to follow certain order. The order is important. Okay, all right. Yeah. So the order we are going to follow, bottom up. Okay, bottom up. Yeah, that order. Then in the same level, from right to left, you start from the, in one particular level, you start from the rightmost local triangle. Yeah. All right. So when we start the last triangle, okay, no violation. Okay, no violation. Yeah. So then we move to the next local triangle. Then we find one violation. Okay, I put a star there. Yeah, that star means one violation is detected. Then we run the local heapify operation. Okay, local heapify operation. Yeah. Yeah. After that local heapify operation, we fix it. Then we move to the next, because bottom up. After you finish this level, you move one level up. One level up, you start from the rightmost triangle. Okay? Yeah. So you detect another violation. So the star, another violation. Okay? Then you run that local heapify operation on this triangle. Yeah. So after you fix it, then move to the same level, you move from right to left. The next local triangle here. So you detect another violation. Okay? Then you run local heapify operation on this local triangle. Yeah. So you fix it. Yeah. Because you follow that path. You fix it. Then you move one level up, another triangle, another violation. Yeah. So you move down, like that. Local heapify. Okay? All right. Yeah. So then move one level down, still dirty, another level down. Okay? Yeah. Then after you hit the bottom, yeah. Then because this is the last triangle, right? Because you hit the top, last triangle. After you finish that last triangle, you are done. Yeah. You complete whole building process. Yeah. So this is a max heap. The whole building process is done. Yeah. So then, not too complicated, right? Yeah, not too complicated. Okay? Yeah. All right, But the next question is, when you do this process, when you do this building a heap process, how much is the cost? That's important. How much is the building cost? If it's too expensive, then your heap sort could be very slow. Because in order to apply the heap sort, you need to build a heap first. Build a max heap first. If the building cost already n squared, then you cannot continue, right? Yeah, this building cost already too slow because n squared. That's already the bottom. Yeah, the worst thing we can get for a sword. The worst thing. Yeah. So the next thing you need to do, you need to estimate the building cost. So we need to estimate. Here you can see pretty complicated, right? The scan, all the levels, beginning, end, all the levels. How do you estimate the number of comparisons? Yeah, because swap and comparison, pretty much same number. So we only need to count the number of comparisons we need. All right, total number of comparisons. Adding up all the number of comparisons to build a max heap. All right. So, but that part, I leave it to next class. But that part, because we need to do the counting level by level. Level by level. All right. Then, so here I want to do one important example. Find the second largest element. Do one example, because in this our current homework assignment, there is one question we need to use this result. One of the questions. you need to use this result. So I want to give you the formula, derive the formula. Yeah. So when you need it, you can use this formula. Okay? Yeah. All right, so let me explain how to solve this problem. All right. Find the second largest. The largest, we know it. N minus 1. Optimal. Now, how to find the second largest? With the minimum number of comparisons for the worst case. That's our goal. Okay? All right. By the tournament method. So here, let's review that tournament method. All right. All right. Yeah. So many students, when I did the grading of the midterm, I noticed many students didn't use the tournament method. A lot of places, a lot of situations, you need to use the tournament method, but those students skip that part. Here, let me just give you a few examples to show you the common problem. So why, when you skip the tournament method, you use more comparisons. Okay, all right. Remember, so our first hard question, we have 5 hard questions in the first one. Our first hard question of midterm part C. Okay, all right. Remember 7 elements, right? X1 not equal to minimum, right? X7 not equal to maximum. X2 not equal to both maximum and the minimum. Then we need to find what's that? Both maximum, minimum, right? Yeah. All right. So 7 elements. Okay? Yeah. So go find max and min. All right? Yeah. So let me tell you. So many students did in this way. So then you use more comparisons than necessary. All right. So, all right. Winner, loser, that way, right? But those students use some simplified version. All right. So, what elements are qualified for maximum? So let's look at the max. For the first step for max, now we want to find the max. Qualify for X4. All right. I use X4. Okay. All right. So X4 not qualify for max. Throw away, elimination. But for max, candidates. X1 qualify, right? So X2, X3, X5, X6 qualify for max. Okay. For minimum, candidate. Yeah. X2, X3, no X4, X5, X6, and X7. Okay? Qualified. Yeah? So they do it in this way. So many students did it in this way. All right? Then, finding the maximum from the first group, because 5 elements, 4 comparisons, right? And find the minimum from the second group, 4 comparisons. Then they add up total 8 comparisons. Yeah, this is the most common mistake. Okay, yeah. The problem is yeah. Look at this. Look at these 4 elements in the first group, and the same group of elements also appear in the second one. Overlap, all right? The overlap. Yeah. When you do comparisons, that you didn't remove the redundancy, because this overlap will cause the redundancy. Redundancy. Yeah. When you do comparisons, for here, part of comparisons you wasted on the redundant part, redundant, overlapping part, redundant. Because the same comparison you don't need to do twice, right? Think about, when you find the maximum, you may compare 2 and 4, 3 and 5. You already did in the first round. Why you do the same thing in the second round? Okay? Because the second round at the bottom, you may do same comparison again, right? Yeah. You should not do that. Okay? Yeah. So the one thing you need to remove the redundancy. How to remove redundancy? You want to make sure in these 2 groups there is no overlap. These 2 groups. No overlap in these 2, no redundancy, right? When we do comparison, nothing to do with the other group. Yeah. The question, how to remove redundancy? By the tournament method. Okay? Yeah. So the typical method used, removing, yeah, so here, the tournament method. Tournament method. Okay? Remove the redundancy. Redundancy. Okay? All right? Yeah. All right. Specifically, yeah, we pair element 2 and 3. Okay? All right. X2, X3, we pair it. Yeah. Okay. And X5, X6. Okay? We pair it this way. And we can assume, larger. Okay? Larger, smaller. But we need a 2 comparison here. In this tournament round, we need 2 comparisons. Yeah. 2 larger, 2 smaller. But after that, then the winners group, the losers group, this time we update. Yeah. Winners group, yeah. Candidates, we put a winners group. Yeah. So X1, X2, X5, right? Yeah. The losers group, X3, X6, X7. Okay? Yeah. Then you see no overlap. In these 2 groups, no overlap. Then with the comparisons, no redundant comparisons. No redundant comparisons. Okay? All right. So then, to get the max, 2 comparisons for max. Here, 2 comparisons for minimum. Total 2 plus total 6, right? Total 2 plus 2 plus 2 equals 6 comparison. You save 2 comparisons from 8 to 6. By the tournament method, you can save 2 comparisons. In this example, you can see the importance of this tournament method. Okay? Yeah, so many students. This is one of the, another question also. Yeah, another similar question also we need to use the tournament method. Yeah, tournament method. Yeah, several. Yeah, I noticed. Yeah, several methods. We need to use the tournament method. Yeah. Okay. Yeah. Yeah. So don't forget that tournament method. Okay. Yeah. All right. Here, let me use this tournament method to solve this second largest. Yeah, that example. Yeah. All right. Yeah. So I have 20 minutes. Let me complete that example in 20 minutes. Yeah. All right. Now we want to, so given array x1, x2, xn. Yeah. Find the second largest element. The question, okay? All right. All right. When we start the first round, yeah, apply the tournament method. Okay? Yeah, first round. Okay? Yeah. All right. Yeah. So let's try to pair. Okay. Yeah. Because here, n could be even, could be odd. When you run the tournament method. Yeah. So here, when we run this tournament method, our goal we want to find that max. We want to get max. When we run tournament to get max, we need many rounds, right? Yeah. Yeah. Right. Many rounds in the tournament method. Okay. Elimination. The champion, the final champion. The final winner. Yeah. So you really need to get the final winner. Yeah. So many rounds of games you need to play. Okay. Yeah. All right. But the thing is, it's not easy to address all the details for all rounds, right? Yeah. Because each round, you may have all the number of players, so one player could be idle, move to next round directly without play. Okay? Yeah. And each level you have that situation. It's hard to specify clearly, right? Yeah, very hard. Yeah. Here we do not need to specify clearly. Okay? Yeah. So here, yeah, we just describe in a loose way. Okay? Yeah. Yeah. In some loose way. Okay? All right. Yeah. X1, X2, yeah, the first round. Yeah. Let's assume X1, X3, X4, 3, and so on. Okay? Yeah. The last two you know, it's hard to specify, okay? Yeah. All right. Then, but we can arrange, right? We can arrange, okay? Yeah. How to describe precisely? The question is, that everyone knows how to run this tournament method, right? But the problem is, it's hard to describe precisely the detailed information. That part is hard, okay? Yeah. So we do not need to, you know, do all the details. Yeah. So then next one, X1, you know, all right, you know. So then, but we know the last, you know, final championship game, you know, the last one, there is a final winner, okay? The final winner. Eventually, we will get a final winner, right? Then, tell me, how many total comparisons we need to get a final winner? The first one. This first round, the number of comparisons in the first round. Yeah. It's look, you know, from picture, pretty complicated. How do you know how many comparisons? But we already have the answer, right? In our module 1, finding the maximum. Given n elements, how many comparisons you need to find the maximum? In our module 1? N minus 1. No matter you do, here, tournament, you can do, you know, whatever way you like, but that total number must be n minus 1. Because by elimination, right? You play every comparison, you eliminate one player, right? But at the end, you eliminate n minus 1. You get a champion, that one, eliminate n minus 1, direct, indirect. There is some indirect way, right? Indirect elimination, yeah? Because this player beats this one, but the final winner beat that player. That means the final winner beat this one indirectly, okay? Yeah. So the final champion eliminates all the other players, directly or indirectly. Indirectly still counts, right? Yeah. If you use that view, you eliminate n minus 1. There. That means the total number compares n minus 1. That's the first round, okay? But first round, it's not enough. We need to go to the second round because our goal finding the second largest. So first round, you know, yeah. It's just first round just like a preparation for the second round. Yeah. So this round we treat as preparation for the second round. It's important. The information we collect in the first round, we should not throw away. When we do the second round, we still need to keep the information collected from first round. Otherwise, if we throw away, then we do redundant comparison. We need to do redundant. We don't want to do redundant comparisons. Okay? Yeah. So for that reason, in our second round, we need to inherit the comparison results from the first round. Okay? All right, second round. All right, then we need to do some important analysis work. Yeah. The first question we need to ask, in order to find second largest, let's try to identify the candidates for the second largest. Okay? Candidates. What are those elements that are qualified for the second largest element? Because some elements are not qualified for the second largest. So we can eliminate them immediately. Okay? Not qualified for the second largest. Yeah. So the first step is identify the candidates for the second largest. Okay, all right. All right. Now, this is the critical step. So if we get this step, so we, very close to our destination. Yeah. All right. So in this step, think about this. Yeah. Yeah. Other than the final champion, all the other players are losers, right? Yeah. Yeah, because everyone loses at least once. Loses at least once. Okay? Yeah. So all those n-1, all the remaining n-1, they are losers. Okay? Yeah. So we have n-1 losers. Okay? But among these n-1 losers, we can divide them into two groups. Although they are all losers, but there are different types of losers. Okay? The first group of losers direct losers to their max. Yeah. Because those losers, they compete, they play with the max and got eliminated by max directly. That's the first group of losers. Okay? The second group of losers, indirect losers. Indirect losers. Okay? So these losers, they didn't play against the max directly. They do not have a chance to play with the champion, the final champion. They do not have a chance to play. Before they can play against the champion, they are eliminated. Okay? We understand in this way. Okay? All right. Yeah. So after we do this characterization, two categories. Now we claim the candidates can only appear in the first group, not the second group. Okay? Yeah. So the first group, the first group is the candidates. They are the candidates. The second, not qualified. They do not have chance for the second largest, not qualified. Can you see this? Yeah, this important statement. Yeah, because the second group losers, let's select one, arbitrary one from the second group. This player was beaten by another player, but that player got beaten by max. Okay? Look at that. Okay? This one, let's call it A. Okay? A beaten by B, but that B is beaten by max. Right? How this A can be the second largest? Because B is higher than A. Yeah, right? B has chance to be the second largest, but the A cannot. Okay? Right? So based on this observation, we can eliminate the second group of losers. So the candidates can only be the first group of losers direct losers. So our next question, we need to count the number of direct losers. Next question, count the number of the direct losers. Okay? Yeah. How do we count? If we can count, we're almost there. Okay? If we can count, we're almost there. Yeah. The question, how do we count? Yeah. So let's look at this tournament, the diagram here. Okay? All right. At each round, direct loser, okay? We need to count the number of games this max player plays, right? Each round, only one direct loser, right? Yeah. Second round, second direct loser, and so on, right? The last round. Right? So we just need to count the number of rounds. How many rounds? Okay? Yeah. How many rounds? Yeah. Yeah. The number of rounds. So that this number equals the number of rounds played. Okay? Number of rounds played. All right? Is it related to log base 2 of n? Log base 2 of n, right? Yeah. Divided by 2, okay? Yeah. Every round, approximately 1/2 player eliminated. Okay? Every round, the number of players eliminated by each round divided by 2, approximately. Divided by 2, divided by 2, divided by 2. The last round divided by 2, that's 1. Okay? All right. So the number of rounds, it is the ceiling function of log base 2 of n. Ceiling function. Okay. Because we need to round it up. Okay? When we take a log, we need to round it up. Remember, there is, some players idly moving to next round directly. So that's why we need to round it up, right? Yeah. Round it up, not round it down. Okay, round it up. All right. So this many direct losers, they are the candidates for the second largest. How to find the maximum from this many players? Yeah, this many players for the largest. Yeah, that number minus 1, right? Yeah. So that number is this number minus 1. So the second round, we need this number minus the first one and minus 1. We need to add these two numbers to get a final total number of comparisons. So the final total number. These two numbers adding together. And plus ceiling function of log base 2 of n minus 2. Okay. That's the formula. So the final formula is this one. Final formula. Okay? N plus log base 2 of n, ceiling function, then minus 2. Second largest element. Okay? Second largest. Yeah. If you need to find the second smallest, the same formula, right? Yeah. Second smallest, the same formula. Okay? All right. After you get this formula here, I just say one of our homework to be, HW2B, one of, here I do not tell you which one, okay? One of the questions, HW2B. It's hidden, it's not that obvious. You need to detect it, okay? One of the questions, you need to apply this formula. But I do not tell you which one. Yeah. So you need to, find it, okay? Find it, then you apply this formula, you get the answer. Okay? All right? Yeah. Okay. All right, so let me see. Yeah. Yeah, so, yeah. Let's stop right here. Yeah. Yeah, so you can, try to work on the homework assignment as much as you can. Oh, next week, let me tell you next week. Yeah. Next week, we have 2 classes before the deadline, right? Homework assignment, there is a deadline. So in those 2 classes, you have a chance to ask me questions, okay? So when you have a question, you bring up. So I will give you hints in those 2 classes, okay, to help you do better, okay? Yeah.